but you should know what it means to be strong. If you put one of those acids in water, each molecule of acid will react with water. Now that's not technically true, but for the purpose of calculations and the number of sig figs you're normally working with, you can assume that 100% of the molecules of acid you put in will react with water, and as acids they will put one of their H pluses onto a water to make H3O plus. So since that reaction is complete and the reverse reaction in that equilibrium is not really significant for calculating things, that's why we consider them strong acids. For strong bases, I think these are also on the formula sheet. Not completely sure about that, but the pattern that we recognize strong bases, if it's not on the formula sheet, what you need to know is the strong bases, there are more than just these, but the ones that you need to know about would involve some metal combined with some number of OH minus molecules. So if the metal has a plus charge, then it's just that metal and one OH, because the OH has a negative. If the metal has a plus 2, then you need 2 negatively charged OHs to balance out the charge of the metal. So as strong bases, when you have an ionic substance, we're going to talk a lot about this more today, ionic substances, for them to be strong, they have to be able to dissolve in water. And what we're going to see today is a nice discussion and visual, some simulations that describe when you have ions, those are held together by pretty strong attractions. But if you put that in water, we can separate the ions because water molecules, being polar, have the ability to surround with a partial charge the ion's full charge. So that's an ion dipole attraction. And you might say, well, this is only partial charge attracting a full charge. Shouldn't the full charge attraction be more, and shouldn't that cause these ions to stick together? Well, sometimes that's true. So we'll see later that some ions don't really dissolve well in water. The stronger the attraction, the less soluble. The stronger the attraction between the full charges, the less soluble it will be in water. But many ions will dissolve because I don't just need to make one dipole attract this ion. I can bring in multiple water molecules, partial charges, and so I have many ion dipoles. They're weaker because there's only a partial charge, full charge attraction, but I have many of them, so that's a pretty decent attraction. Plus, just the motion and the collisions involved in a liquid can generally cause attractions to tend to break up a little bit. So, because this produces an OH minus, which is a strong base, because an OH minus has a full negative charge, and its negative charge allows it to very nicely share a pair of electrons with an H plus, which is what the role of the base is in a reaction. That's what makes compounds that have free OH minuses in solution bases. So strong bases. What about this compound? Would you consider that to be a strong base? No, because if you look at the Lewis structure, since the carbon is sharing electrons with the oxygen and not the metal, the carbon is a nonmetal and it's much more willing to share. It can accept the electrons from the oxygen, share fairly strongly with the oxygen, and so the oxygen only has a partial negative, and so it's not going to be like an OH minus with a full negative, the oxygen with a partial negative doesn't attract an H plus and accept an H plus very readily. It can. It could be a pretty weak base, but a strong base is one where if I put it in water, it has the ability for all the molecules to react. And so I really need a full negative for something to be considered a strong base. If I had this, this would be a strong base because now I have a full negative on my oxygen. And if that comes in contact with water, it will pick an H plus up from the water to balance out its charge. So most strong bases have a full negative because the negative allows them to attract an H plus. But it has to be a pretty unstable negative. Like a Cl minus obviously is not a strong base. It doesn't have an unstable negative. To be unstable, as we've talked about earlier in the semester, a charge needs to be on a smaller atom or a less electronegative atom. So generally, for strong bases, what I expect you to know is this pattern here, and to be able to explain what the role of the base is in the reaction, what it means to be strong versus weak.
For strong acids, would they always be considered strong electrolytes?
Yeah, if something is a strong acid or base, it's also a strong electrolyte, because if something is a strong base, for every molecule of that base I put in, when it reacts with water, I will get, if it's strong, that means the reaction happens effectively 100%, I will get OH minus, and I will get one OH minus for every one base. If it's a strong acid, for every one acid I put in, which we usually abbreviate HA because an acid needs to be able to donate an H plus, when I put that in water, if it's strong, it will react basically 100%, and the H plus will be pushed onto the water to produce H3O plus. And so when these are balanced, usually it's a 1-to-1 ratio. And since it's strong, I won't have any of this left over after the reaction is done. Everything gets converted into products. So what it means to be a strong electrolyte, which we'll talk about more today, is that you produce charges in solution. An electrolyte produces charged particles or ions in solution. And so as an electrolyte, what that means is when you produce ions in solution, those ions are free in solution. They can move around, and what electricity is flowing charged particles. So solutions of ions can conduct electricity. So since if you take, normally you have electricity flowing through a wire, right? You have like a copper wire. You connect that to your outlet, and the electrons, negatively charged electrons, flow through the wire. But a solution can also allow charged particles to flow if the solution has charged particles or ions in it. So since strong acids and strong bases produce ions stoichiometrically or quantitatively, or one ion for every one molecule that I put in solution, that makes them strong electrolytes because the number of molecules of acid or base I put in will eventually, when it all fully dissolves and reacts, produce that same number of ions in solution, which can carry the flowing charge through solution and conduct the electricity. So strong acids and bases are also strong electrolytes because they produce quantitatively a number of charged particles equal to the number of original uncharged particles that I put in solution.